going to take a look at from homework number 5, question 25. So I'll let you read through it. Maximum leg strength, studied cycling performance before and after, 8 weeks of leg strength training. 7 previously untrained males, so that probably is important, it's a number, right? Performed leg strength training 3 days per week for 8 weeks. So it's kind of the treatment, but they've got numbers there, so it's underlying them. 4 sets of 5 replication, a lot of numbers. Again, this is the treatment that they're going at 85% repetition maximum. Peak power during incremental cycling increased to a mean of 315 watts. So there was an increase with a standard deviation of 16 watts. And we're asked to construct a 95% two-sided confidence interval for the mean peak power after training. Okay, so it looks like we've got to get the thing. So how many did we have in our sample? We had a sample of 7 untrained men. We need for this calculation to find the mean, which it was given, so it increased to 315 and had a standard deviation of 16. So since we are looking for a 95% confidence interval, remember that'll be that it involves the mean, and we're going to add and subtract this sort of formula, the t-value times the standard deviation divided by the square root of the number, and then the mean is less than or greater than. It's in the middle of this stuff. So what do we want? We want a 95%, so we want two-sided, so that's alpha is 5%, but since it's two-sided, we divide it by 2, so we're looking at a 0.025 for our alpha, and our degrees of freedom, since we've got 7, our degrees of freedom are going to be 6, so that's what we're going to have to look up. 0.025 degrees of freedom are 6. And we've got everything else in here. And again, remember we're setting up that our mean, our population mean, is between these two numbers. So we've got our mean, 315, and we've got 315 over here. We're going this bottom side we're going to subtract, this top side we're going to add. That's why we get it. So let's look up this t-value for 0.025 and 6 degrees of freedom. Okay, so we pull up our statistical tables. We're looking for the t-value. These are z tables. T tables. So we've got a degrees of freedom of 6. Squared t. Okay, here we go. T of alpha v. This is the one we want. Yeah, it's a chi-squared. Okay, so t, 6 degrees of freedom, 0.025. So that's a two-sided test at that. So 2.447. 2.447. So the t-value is 2.447, 2.447 times by the standard deviation over the square root of 7. Standard deviation over the square root of 7. And we just multiply these out and then subtract from 315. What we end up getting is 300.6 0.202, which is less than or equal to mu, which is less than or equal to 329.798. So that's how we get a confidence interval. And again, we are now 95% of the samples should be between here. So it gives us that it's sort of a way, is what that's saying, of the sample means would be in here. So it's an estimate, gives us a good solid estimate of what the population mean should be. Of course, we could narrow this down if we had a larger sample, because again, we're dividing that out. But anyway, this is what we got. Larger sample would make this a smaller number, which makes that a smaller number, and so you get closer and closer to this interval. Okay, so that was homework 5, number 25. Keep on going, and we're still in the same homework. So number 27 this time. 27, we have some information here. Presidential election exit polls from the critical state of Ohio provide the following results. There were 2,020 respondents in the exit poll. What's the sample size? And 768 were college graduates. Of the college graduates, 412 voted for George Bush. Calculate a 95% confidence interval for the proportion of college graduates in Ohio that voted for George Bush. So again, we're going to get a proportion here. Calculate a 95% lower confidence bound for the proportion of college graduates in Ohio that voted for 95% confidence interval. Okay. So what we're going to look at for the A question is we need to kind of, what is the proportion? Well, 412 out of 768 is going to be what we call our p hat. So that's the sample proportion. 412 divided by 768. That gives us that of the college graduates, 0.536 or 53.6 voted. Remember, for our confidence interval, we're going to need the sample size. And again, in this case, it's only 768. Although the larger sample was 2,020, we're just looking at the college graduates. Then the other part we need, since we want a 95% confidence interval, we're going to need to figure out that's alpha 5 and so alpha over 2.025, right? Because we've got alpha over 2. And that's, we could look that up in the Z table, but again, that's fine. Hopefully you remember that number, 1.96. If you look up 0.025, actually, probably easier to look up negative 0.025, because then you'll see that's the percentage you're looking for. Look it on a negative, you'll get the negative 1.96. Anyway, we've done this a few times in class, so that's what we've got. So for a confidence interval, what are we talking about? Well, we're talking about this proportion. And again, the formula is whatever we're talking about, the estimator, we're going to do a plus or minus z of what we're measuring, in this case alpha over 2, and that's 0.25. And then we multiply that by the square root of p, the proportion, p hat, minus 1 times 1 minus p hat, all divided by n. Okay, so we're going to plus and minus that. So to get that, we're going to estimate that the population proportion, notice there's no hat on it, is going to be estimated by 0.536, that's p hat, that's this part here. The lower half gets minus, so 0.536 here. The top half is going to add on to that. Our z value is 1.96, and then we multiply that by the square root of 0.536 times 1 minus that, which is 0.464. I'll have more room over there. All divided by n, which is 768. Okay, so upper here we got 1.96. We're going to add that. Square root 0.536. 1 minus the proportion, which is 0.464. All divided by 768. We do the math and we find, give ourselves some more room too, that our population proportion, the 95% confidence interval, is 0.501 to 0.571. So proportion in the general population should be there. We're going to go through basically the same process, except that we're doing a lower confidence bound, so 95%. We want to see what would be the bottom number we would expect, and so that 95%, that's a z of alpha 5, it's at the bottom half. So for the b part, the only thing that's really any different is that we're doing a z, a one-sided 0.05, and for that, that's the 1.64. Okay, and it's the lower bound. It's the lower bound, so that's the bottom half. And so we do the same thing here. We've got basic, well, let's go. Then our estimator is going to be p hat minus z of alpha square root of p hat 1 minus p hat all over n. Okay, so that's going to be the lower bound for p. So we just do that. And again, we've done most of the calculations. If you did this part here as a separate calculation, all we got to do now is multiply by 1.64. So we've got 0.536 minus 1.64 square root 0.536 times 0.464 divided by 768. That's got to be less than or equal to the population proportion, and that gives us 0.506 is less than p, no hat. So let's be able to do those type of problems, and then now let's jump to homework number 6, look at an example from there. Okay, so the life in hours of a battery is known to be approximately normally distributed with standard deviation alpha equals 1.25 hours. A random sample of 10 batteries has a mean life of 40.5 hours. So now we're asked, is there evidence to support the claim that battery life exceeds 40 hours? So we're seeing if we're going to exceed 40 hours. Sounds like a one-sided test. And again, what we do here is we want to set up sort of the 7 steps. So we'll start with, what's the first thing? What is the parameter of interest? Well, it's the mean battery life. of the population. So we're looking, that's really what we're looking for. Setting up our hypothesis, our null hypothesis is we would make the assumption, well, that the mean is actually equal. Is there evidence to support the claim that the life exceeds 40 hours? So the null is that it would be equal to 40 hours. Not, you know, but yeah. So the alternate hypothesis number one, I guess, is that the mean is actually going to be greater than 40. And so those are those two. What we're going to use is that we're going to measure the z-value, and that we're going to use the sample mean minus the assumed population mean divided by the standard deviation over the square root of n. So we'll do that calculation. And then when do we decide to reject? Well, we reject if we reject h naught. What are we rejecting? We will reject h naught if our measured z-value is greater than the z-value of alpha, the test. And we're using a 0.05. It's a one-sided test, so it'll be what, 1.64, 1.65, right? Z of 0.05. One-sided test is 1.65. Okay. So let's go ahead and do the calculation. Z naught is going to be equal to, scroll up a little bit, the average is 40.5 minus the assumed population average, 40, divided by standard deviation that they gave us was 1.25. It's right there. And we're going to divide that by the square root of the sample size over 10 batteries. Okay. And if you do the math on that, you should get 1.26. Now, what does that mean? Again, what this is saying, the z of 1.65, remember if we look at the normal curve, here's the mean, which a standard score would be 0, but for our data is actually 40. 1.65 is over here, so on the positive side, right, it was greater than we're looking, so 1.65 would be like here, a z-value 1.65. We've got a z-value 1.26. Well, where's 1.26? Well, it's, there's maybe one. It's like here. 1.26. Did we make it into the rejection region? No, we didn't. We didn't make it above, right? We need z naught to be bigger than z of alpha. So we can't reject. We do not reject. There's not sufficient evidence. Okay. Is there evidence to support the claim? No. So do not reject H naught. There's also supposed to be a B question in here. It says, what is the p-value for the test in part A? I don't think I got it copied in here, but I'll go ahead and do that. So the p-value. Well, a p-value is going to be 1 minus I'm not quite, that's a phi or something, of the z-score that we got. We got 1.26. And what we're going to see is that this value is going to be greater than 0.05. So this is a way we can check the alpha, right? So what we have to do is go to the table, look up 1.26. Let's do that. Let's see, where's my table? I think my table's here. We go to the z table. We're going to look up 1.26. Here's 1.2. Here we go. 0.6. 1.2. 0.6 is 0.8962 if you round it. 1.8962. Oh, sorry, 0. Can't have 1, that'd be 100%, right? 8962. And when you subtract that, you get a p-value of 0.1038. And again, that's greater than our alpha value. We need to be smaller than 0.05 to reject. We're larger. So this also confirms that we do not reject. Okay, so whether you directly look at the z values up here, I mean, we can do that for the test. Z values doesn't exceed that, or if we go to the alpha value, the p value compared to the alpha, both of those are ways of checking. Okay. So we've got 2 more to go through, and then so we'll look at homework number 6, number 28, and we've got 2 questions to answer on that one. If you look at 28, we have 2 samples. This is going to be looking at paired t-tests. That's the next one, sorry. We've got 2 samples. The overall distance traveled by golf balls tested by hitting the ball with iron. Byron, a mechanical golfer, swing that is his champion, Byron Nelson. 10 randomly selected balls of 2 brands are tested and the overall distance measured. Assume that the variances are equal. The data follow. Is there evidence to show that there is a difference in the mean overall distance of the brands? Use alpha equals 0.05. So again, we sort of go through the 7 steps with this, and then we'll calculate the confidence interval. So the first step is, what are we looking for? So we are looking for a difference in the means. Is there a difference between the 2 different brands of balls getting hit further? So we would say, and that's our populations, that mu1 minus mu2 is equal to some delta, which we're going to say 0, that there is no difference. So our first hypothesis is that the difference is 0, or if you want, mu1 equals mu2. The means are the same. So the alternative hypothesis, the other one, is that they are not equal. Okay. Our test statistic, because we're dealing with samples, is going to be a t-value. So it's t naught is going to be the mean of the first sample minus the mean of the second sample minus the difference here, which is our delta naught, which is going to be 0. So that's But if we were looking for a difference, there could be a number there. In this case, it would be 0. And then we've got this. Remember this pooled variance. Square root 1 over n1 plus 1 over n2. So when do we reject the null? Well, as long as, let's see, what are we doing? We are doing alpha equals 0.02. The difference, it's a two-sided. So what we're looking up is that two-sided, so half of this, 0.025, and how many degrees of freedom? Well, we look up, since we have two samples, we add them together, it's 20 minus 2, so that's going to be 18 degrees of freedom. So we need to look that up first, and that'll tell us the t-value where we can reject. So if it's either less than the negative part of this or greater than. So let's go look that up on our table. Again, we got to get down here to the t, and this is going to be an alpha of 0.05 with 18 degrees of freedom, 2.101. So if it's when do we reject? Well, if t naught is less than or equal to 2.101 negative, or if it's greater than positive 2.101, that's when we would reject. Or that's kind of a wrong way. If actually if t naught is down here, t naught's not in the middle. T naught would have to be less than this. You know what I'm trying to say. Or it would have to be greater than this. So this, what I did is sort of like a confidence interval thing, but so we either need to be greater than the positive side or less than the negative side. So let's go ahead and do the calculations. What you need to do is, again, but Excel could do this, you can get the standard deviations and the means of this sample, and I'll let you do that, but I've done that in advance. So the mean of the first, actually let me put that up here. So x bar of the first ended up being 275.7, and the standard deviation of that ends up equal 8.03. The mean of the second sample is 265, and yes, there is a difference between these two means, but what we want to see is, can we say that that relates to the population? But notice it's got a standard deviation of 10.04. This has 10 and this has 10. Okay, and we need to calculate this pooled standard deviation. Let's see if I can have enough room here. Gonna go up a little bit more. So the pooled, I guess we'll do that over here. For that, we use the formula, the square root n1 minus 1 times the standard deviation 1 squared plus n2 minus 1 times the standard deviation of 2 squared, which is the variance, right? All divided by n1 plus n2 minus 2. So there's our sort of degrees of freedom. Start plugging all that stuff in. You get n minus 1 is 9. 8.03, that's what we calculated, squared, so that's from up here, standard deviation, plus 9, which is n2 minus 1, times its 10.03, just 10.04, squared, all divided by 10 plus 10 minus 2, or 18. Do all the math on that one, plug it in, you should get 9.0927. So now we can come back and calculate this T naught. We're going to go up a little bit higher. So for T naught, x1 minus x2, so 275.7 minus 265.3 minus 0. I'm going to go ahead and put that just as, that's the difference thing there. But I didn't just forget about it. And then we're going to take this number we just calculated, the pooled variance, pooled standard deviation, I guess, because it's not squared. So that's 9.0927. And then that's going to be times the square root of 1 over 10 plus 1 over 10. Calculate that, you should get 2.558. Now, where is this? 2.558 compared to this, T naught is greater. So again, we've got kind of this curve. These are our rejection regions. So if we're at negative 2.1 or positive 2.1, and yeah, 2.5 is going to be in that rejection region. So we can reject the null, and is there evidence? Yep, there is evidence. Okay, we can reject the null hypothesis and accept the alternative that there is a mean difference, that there's a difference between the brands. Okay, so one would have an average as we go forward. Okay, and for the confidence interval, it's basically the same, a very similar calculation, but what we do is we sort of solve, and we use this t value here, and well, let's just do this. So for the B part, confidence interval, so we're going to say the difference in the means, x1 minus x2, and again we're going to plus and minus this, the minus on the lower end, plus on the top end. We take the t that we're testing, and that's going to be 0.025 with 18 degrees of freedom. We take that times s sub p, square root of 1 over n sub 1 plus 1 over n sub 2. So similar to what we've, so it's kind of like the denominator here times the numerator. We're trying to get this, so see, we multiply by this, that's a t naught, or the t value, and then we bring this over. Okay, so just to list all this out, so it's 275.7 minus 265.3, we do that, and then we're going to subtract off 2.101 times 9.09, and that we got up here, you go 27 if you'd like, get a little bit more accurate. Square root of 1 over 10 plus 1 over 10, that's got to be the lower bound, and what's that telling us is the mean, the difference in the mean. populations will be between that and all of this stuff plus. So I'll just say blah 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 plus blah blah blah. Same thing. So all that changes as this minus becomes a plus. And again, when you do the math, this all becomes 1.86. So we take that minus this, we get that. Oops, minus mu2. So the difference in the mean should be somewhere between 1.86, and at the upper end, when you do all this and you add, what we end up with is 18.94. So that's a big difference, right? Could be anywhere from 1 to 18, that the difference in the mean. So it's not a very narrow, but that 95% of the samples is a 95% confidence interval, right? Two-sided. All right. So let's go ahead and look at our last question for consideration. Homework number 632. Two different analytical tests can be used to determine the impurity level in steel alloys. So we're using two, so this is a pair, the samples are the same, they're sampling the same thing using two different tests. So this is a paired t-test. 8 specimens are tested using both procedures, and the results are shown in the following tabulation. Is there sufficient evidence to conclude that both tests give the same mean impurity level at alpha equals 0.01? So this is a two-sided test, and again, we kind of walked through three different things we want to be able to answer here. So is there sufficient evidence to conclude that both tests give the same mean interval? So we'll start with that one. And again, what we're really trying to see is there a difference? So our null hypothesis would suggest that the mean of the difference equals 0. The alternative hypothesis would be that the mean of the difference does not equal 0. So it's a two-sided. Test statistic we're going to look at, it's a paired t-test, so that gives us that t naught is equal to the difference in the means divided by the standard deviation divided by the square root of n. Okay. And since we are doing, so what test statistic we're looking at is a two-sided 99% confidence interval, right? Alpha of 0.01. So we're looking at alpha of 0.005, and see, there's 8. So we're going to use 7 degrees of freedom because this is a paired sample. Okay, so we're going to look that one up. What is this t-value? Because that's what we're going to be using. So we're at the t for 0.005 and 7 degrees of freedom, 3.499. That's our test statistic. So if we do all of this, and if it's either greater than that, we can reject, or if it's less than the negative of that, then we can reject. Okay. So let's go ahead and calculate the average, the D bar. And to do that, what you do is you subtract off each of these, right? And then you get that average of the difference. And if you do that, what you should find is that D bar is negative 0.2125. And then you would also find the standard deviation of the difference and again, I'd let you, Excel is really good at doing that, you would find that your standard deviation is 0.1727. We have our n is equal to 8, and so then now we can calculate our T naught. What is our test? So D is negative 0.2125. Standard deviation is, the difference is 0.1727 divided by the square root of 8. And if you calculate all this, you should get negative 3.48. Now, what's the deal? Well, can we reject that? Well, we would reject if it was less than negative. Is this number, put a question mark, is it less than negative 3.49? It's not. This is more negative than that. We're close. We're sort of like almost to the boundary, but we selected this 99%. Had we selected a 95% confidence interval, so if alpha been 5%, we would have been probably able to reject, right? But at this test statistic, we are not able to reject. Okay. So we failed to reject. Again, maybe we go back and say okay, at a alpha of 5 we could do it, but no, not alpha of 0.01, no. So what is a statistic value? We actually answered that here. Statistic value is negative 3.48. So the answer is, can we reject it? No, and the reason is because the test statistic is not in the rejection region, right? If we were to, this is normal curve, but t-value is kind of similar type idea. So this is negative 3.49, and positive 3.49 way out there at the ends. The rejection regions are out here. That means that it's not by chance. We're just change it because we're so close. We're like really close to it, but we're on this side of the wall. We're in the non-rejection. We're in the confidence interval. So negative 3.48 is right there. Okay, so confidence interval, again, we kind of think of this is T naught. We're going to use the T measured value. So what we're really trying to find out is this interval, let's go to blue. We take our T of our alpha, we're going to multiply it by the standard deviation of the difference divided by the square root of n. Okay. And we're trying to see, that makes an interval. This will be the negative side, and this would be the positive side of that same thing. So D square root of n. Okay, yeah, I was thinking about to the golf ball one. Okay, so what do we got? Come back to here, 3.499 times standard deviation, 0.1727 divided by square root of 8, less than or equal to the difference in the means, and do the same thing here, 3.499 times 0.727 divided by the square root of 8. This will be the negative side, that'll be the positive side. And when we do that calculation, oops, I just cleared it out. No, came back. Good. I got negative 0.2136 less than or equal to positive 0.2136. So that's our confidence interval, and notice the d value for this particular sample is down here. It's close to this border. If you were to round it, it would be 2.13, but it's 2.2125. So it's off very little, but it's not in the rejection region. It's still in this confidence interval that's acceptable mean, right? On the other side, it would be up here. So if the other balls, the other impurity, I forget what we're measuring here, but anyway, that's our 95% confidence in, not 95%. This is what are we doing? We're doing a 0.01 alpha, so this is a 99% confidence interval. Now the question didn't actually state it, but since that's the alpha that we were using up ahead, right? Alpha 0.01, so that's a 99%. All right, review the rest of the questions, and if you've made it this far, I thank you for watching all the way through, and these are the ones here that you're going to want to kind of keep working through, and then you'll be well prepared for the quiz when we get back. Thanks.